All right. So, our last task is to consider 2 degree of system for 2 degree of freedom for this system. To get 2 degree of freedom of this system, what I will do, I will add this additional mass and spring to the system. Now, the information on the stiffness of the spring and the mass are given in your handout. So, you can have that information. Okay. Now, when we consider this whole thing as a 2 degree of system, there is again another assumptions that we ignore the mass is being twisted. We just assume that the spring and mass is moving in vertical directions. Okay. So, that means this beam is moving in an angular directions, and this spring and mass is moving in vertical directions, and that is why we consider this system is a 2 degree of system. All right. So, for force 2 degree of system, okay. So, we will just consider the same concept that we consider for force single degree of system. Okay. So, we will consider capital omega, or which is a external force or excitation frequency for 3 different values. Okay. So, first of all, we will consider maybe 0 and then omega n. Now, because this is a 2 degree of system, there will be 2 natural frequencies. So, we will consider 2 natural frequency omega n 1 and omega n 2, and when it goes to infinity. Okay. Let us draw this diagram again, where x axis represents force frequency in hertz, and in y axis capital P, which is the amplitude in it would be in radian. It would be in radian. Okay. So, at 0 value, which is the first case, at 0 value the amplitude would be also 0. Let us consider this is first omega n, which is the first natural frequency of this force 2 degree of system. The system will again have infinite amplitude, and let us consider the second natural frequency is omega n 2. Again, at this frequency the amplitude will be infinity. In between these 2 natural frequency, there will be a one point where the amplitude will be 0, and at that point we name it as null point. Okay. So, in between 2 resonant frequency, we will have a point where the amplitude will be 0, and then once we pass the second natural frequency, the amplitude will be, which is we consider as omega tends to infinity, that means a bigger number of natural force frequency, the amplitude will be constant or will have small value, but importantly it will not be 0. So, that is our expected or theoretical response from the force 2 degree of system. Now, we will see exact same way applying the values on the system to see how the system behaves. In this case, again we will fill up the table exactly same way. So, the first column, that means frequency of the exciter, and the third column frequency of the beam will be exactly same. We need to fill up the maximum amplitude that we get from the small window. Alright, so we will start from again from 5 hertz, and then we will continue till 12 hertz and then jump to 20 hertz. Okay. So, at 5 hertz you can see how the system behaves. So, this is at 5 hertz. I need to actually stable the system a little bit, and then you can just look at the amplitude, which is 1.2 millimeter. Okay. And then I will just increase the to 6 hertz slowly. So at 6 Hz you can see this amplitude started to increase, which is 5 millimeter at the moment. At 6.2 you can see the amplitude rise to 8 millimeter and it vibrates to, now it stables. Okay. Alright, so that means we get our first natural frequency at 6.2 Hz. Then I will increase to 7 Hz. At 7 Hz the amplitude is 0.6 millimeters, which is expected. Once we pass the resonance frequency, the amplitude again started to reduce, and that's what we see here. Then increasing to 8 Hz. At 8 Hz, still the amplitude is small, even smaller, and now it's 0.3 millimeter. I'm going to increase to 9 Hz now. So at 9 Hz, the amplitude becomes 0.2 millimeter. Now, if I can just very quickly show you, if you can just look at the beam, literally, even though the spring is vibrating, but the beam literally is not vibrating at all. So this is the null point. Okay. Even though at theoretical perspective we consider the amplitude will be 0, in practice we didn't get 0, but it's close to 0. Again, we want to increase the frequency to 10 Hz. What we now expect is to increase the amplitude, and that's what we find. Now the amplitude is 0.5 Hz, 0.5 millimeter. I'll try to stable the system a little bit. Next one is going to 11 Hz. Alright, at 11 Hz we get the amplitude 4 millimeter at the moment. So at 11.2 we get the highest amplitude, which is 6 millimeter. That means that is our second resonance. Alright, then we increase it to 12 Hz, and I'll try to stable the system again. Okay, at 12 Hz the amplitude again start to reduce to 2.5 millimeter. Okay, so then that is our 12 Hz, and then we'll jump to 20 Hz to see how the system behaves. Okay. Now 20 Hz, which we consider the exciter frequency tends to infinity, as we expect that this will not be 0, the amplitude will not be 0, but it will be a small value. And if you just look at the window, the amplitude is 0.5 millimeter. That means it stays certain small amplitude, but it doesn't goes to 0. Okay, that means vibration is still there, but it doesn't stop the vibrating the system. Okay, and that is the end of our last task. Couple of information from this task is that, first of all, when we have 2 degree of system, we have 2 natural frequency. That means we have 2 resonance, and that means as long if we have multi degree of system, we will have multi resonance, and that means we need to careful to avoid those natural frequencies. And why natural knowing any system's natural frequency is important, because we want to avoid the resonance, and resonance could be if we cannot avoid the natural frequency or resonance, it could harm the system. Two classic examples of resonance is that one is Tomoka Bridge, which was broken due to the a wind was blowing, which is considered as an external frequency, and that frequency of wind is equal to the natural frequency of the bridge, and when these two frequencies are equal, they create a bigger amplitude, and that is why that bridge was broken. Another one was when a bridge Another example is that a group of soldiers were marching on a bridge, and the frequency of that marching soldiers are equal to the natural frequency of that bridge, and that creates resonance, and that is the reason that bridge was broken. So, this is the very classic example, but overall the lesson from this vibration prac is we want to know natural frequency of the system. Once we know the natural frequency of the system, we can avoid the natural frequency, and we can use even higher frequency without damaging the system. That is all. Thank you.